perpendicular to the page here. Just we have a current coming, how about up out of the page? Well, first, let me do it this way. Let me do a no current. All right, so let's put some compass needles around here. Where are they going to point? They're going to point towards the north pole of the Earth, which is, we'll make it over here somewhere. So if we have some compass needles here, they're going to align themselves in this orientation. Okay, with the Earth's magnetic field, whatever the strongest magnetic field in the area is. We turn on that current, and they align themselves this way. So what happens is that the magnetic field produced by a current-carrying wire encircles the wire. It forms a circle around the wire. What direction does it point? We have a right-hand rule for that. This is our second right-hand rule that we're learning. You put your thumb in the direction of the current, and you let your fingers kind of roll around the outside of the wire, and that's the direction the magnetic field points. So in this case, if I put my thumb in the direction of the current, my fingers roll around in the counterclockwise direction. So that's the way the magnetic field line points. I would draw a magnetic field line as a circle around the wire. I would draw it like that. Of course, just like electric field lines, the field, if you're standing at some point over here, if you're standing right here, what direction does the field point? Tangent, right? The field points that way. If you're standing over here, the field points this way, right? It points tangent to the curve. If you had your compass out at one of those places, that's the way it would point. So that's why the compass needles point like this. But we draw the field lines as circles, just like we would with electric field lines. And at any point on that line, the field is tangent to the line. So we used Gauss's law with electric charges, and it told us something about the fields, right? We knew there was a relationship. If we had a black box, we didn't know what was inside of it, but we could measure the electric field all around the box. We knew something about the charges inside. And so we figured we could go backwards. We figured if we knew about the charges inside, we could figure out something about the electric field, right? Gauss's law helped us link the charges inside to the inside some enclosed surface, right, to the electric field that surrounded it. And so we have something similar here. It's called Ampere's law. And instead of a surface, an enclosed surface, it's just a loop, an enclosed loop, a closed loop, I should say. A closed loop, and we run it around a current-carrying wire. And just like Gauss's law, it only helps us find the magnetic field, and it always is true, right? Gauss's law was always true. But sometimes it was really messy. We had other ways that were better to find the electric field. Sometimes it was really, really clean and it gave us a nice answer, right? In a very limited number of cases. This is the same with Ampere's law. Ampere's law is very similar to Gauss's law. In certain cases where there's nice symmetry, it helps us find the magnetic field really nicely. And so what it tells us is if we add up all of the magnetic field components that are parallel to our length, B parallel to the length, and we add them all up, you're really integrating B around some path is what you're doing here. But we'll just talk about it in terms of adding up the parallel component to some length element all the way around. It's going to be some constant times the current enclosed by the loop. So if in a case where we know the magnetic field is constant all the way around and it's always parallel to the length, like a circular path around a long wire, then what we get is B times the length of the wire is mu naught I. Okay, so if we have an infinite straight wire with current I, we have that situation. The magnetic field is all parallel to our length element as we go around. So we can just call it B times our length element. And if we add up all the little segments, we just get B times the length is mu naught I. And so what does that tell us? That tells us that the magnetic field, some distance r away from a current carrying wire, is mu naught I over 2 pi r. Okay? The magnetic field, some distance r away from an infinite wire carrying a current. So that's one that we'll use a lot. And once we know this, then we can figure out things like the forces between two current carrying wires. Two current carrying wires exert a force on each other. And we can figure it out. What do? We say one of the wires is filling the space around it with a magnetic field. We've got the formula right here for the magnetic field that it creates. We say the other wire is sitting in that field. So let's just do it. Two long wires. You want the currents to be same direction or opposite direction? Same direction, okay. I1 and I2. So I1 is creating a magnetic field. What's the magnetic field? And we need some distance between these things. How about capital D? B is equal to mu naught I1 over 2 pi D, right, at location of I2. Now we have a current carrying wire in a magnetic field. And it's going to feel a force. I L B times the sine of the angle between them. But in this case, it's 90 degrees, right? So if these are infinite wires, let's find the force per unit length. It's I times I2 times mu naught I1 over 2 pi D. So we can find the force between these two wires. Is it attractive or repulsive? what direction is the magnetic field created by I1 at the location of I2? I1 is going to the right, so I'm going to put my thumb in that direction. And everywhere underneath, the magnetic field is pointing into the board. Everywhere above the wire, it's coming out of the board. If I was at a location out here, it would be pointing straight down. If I was behind the board, on the opposite side of the wire, it would be pointing straight up. You see that? So down here, it's pointing into the board. So B would look something like this. I2 is that way. B is into the board, so the force is up. So this is an attractive force. You could reverse all your thought processes, have I2 creating a magnetic field at the location of I1, I1 going to the right, its force is going to be in this direction. And you knew by Newton's laws they had to be equal and opposite, right? These two objects are interacting. They have to interact with equal and opposite forces. Okay, so we'll stop here. We talked about current carrying loops in magnetic fields and parallel wires and charges in magnetic fields, individual wires in magnetic fields, loops in magnetic fields. So go over all that, and we'll finish this chapter next time. Have a good weekend.